Okay, welcome back again, everybody. Today we're doing section 16.3, which is all about the fundamental theorem of line integrals. So let me pull up the slides and we'll get started. Here we go. So another little bit of a fair warning, this lecture might be a little bit long, but at least it's not super technical, I would say. There are some new definitions and some new ideas we're going to talk about, but it's not as technical as, say, section 15.9, the one about the change of variable formula. Here's the overview. So we're going to quickly review the fundamental theorem of calculus part 2. Then we're going to see how we essentially generalize that theorem to get the fundamental theorem for line integrals. Then we'll talk about independence of path, and we're going to spend some time talking about independence of path and how it relates to conservative vector fields. So then we'll talk about what conservative vector fields are. We'll talk about a specific characteristic of conservative vector fields, and then computing conservative vector fields, and then finally how this all relates to conservation of energy. All right, so here's the first bit. You got to kind of dig back into your brain a little bit and think about the fundamental theorem of calculus part 2. So you should have learned this back in Calc 1. This is actually a statement of it that the book calls the net change theorem, but it's an equivalent statement. So here it is. Let f prime be continuous on this closed interval from a to b. Then the integral of f prime, big F prime, from a to b is f of b minus f of a. So this is like everybody's favorite version or favorite part of FTC2. But I've always found that the first part is really the more profound part of the fundamental theorem of calculus. We'll use that a few times today. Um, Generally speaking, what this is saying is that the integral of the rate of change of a function over an interval is equal to the net change of that function over the interval. So it's kind of like the way that I think of it is if you add up a bunch of instantaneous rate of change over a period, then you get the net change of the function over that period. That's really what it's saying. Now what we're going to do is we're actually going to generalize this theorem for line integrals. And what we're going to do is we're going to interpret the gradient of f as a derivative of the function. It's not really much of a stretch because you remember the gradient is the vector of all the partials. So if we kind of view that as a, quote, derivative of the function, you're going to see that the statement of the fundamental theorem for line integrals is pretty much the same as this, but generalized to taking an integral over an arbitrary path. That's the idea. So this is what's called the fundamental theorem for line integrals. Here it is. Let C be a smooth curve given by a vector function r of t. We're going to let f be a differentiable function of n variables whose gradient vector del f is continuous on C. Then what we have is that the line integral of the gradient of f over that curve is equal to the value of f evaluated at the endpoints of the curve and then taking the difference of those values. So one thing is just take a moment and look at how virtually identical this is to FTC2, right? It's like taking the integral of a derivative and then you can evaluate at the endpoints right here, just like this. Same kind of idea right here. So another thing to note here is that since having del f, it means we have a conservative vector field. So we have a conservative vector field, and so what this theorem says is that we can evaluate the integral of a conservative vector field over a curve C just by knowing the value of f at the endpoints of C. And that's really what's so phenomenal about this theorem. Um, I mean, the fact that you only really need info at the endpoints says a lot about the behavior of the function itself. Okay, we're going to prove the case where f is just a function of 3 variables for clarity, but the proof for the n variable case is pretty much the same. So you should try it. It's really not that difficult. It's maybe a good chance for you to kind of flex your mathematical notation skills. The reason that we get clarity by only using 3 variables is because I can explicitly write out the sum that we're going to see without having to use an additional sigma notation. So if you want to try to do this proof on your own for the n variable case, you should, but you're going to have to use a sigma notation at some point in there to talk about adding up n many terms. Right, here's the proof. Let C be a smooth curve and let f be a differentiable function of 3 variables, we'll say, where the gradient of f is continuous on that curve C. Then we want to compute this integral right here. And by substituting in our parameterization of the curve, we can re-express the integrand like so. And then here, if we do this dot product, you see we got a dot product of 2 vectors right here. So compute the dot product. And what we're going to get is partial f partial x times partial x partial t. That's the product of the first two components, right? The respective first two components. Then we're going to add partial f partial y dy dt. That's the product of the second components. And then partial f partial z partial t. That's the product of the third components, right? So this is what we get when we do the dot product. Now we can re-express this using a derivative because this is really just an instance of the chain rule that we learned back in, oh man, I think it was section maybe 13. It wasn't the multivariable chain rule. Somewhere in chapter 13, I think. Somewhere in chapter 13. But this is really the derivative of this composition, f of r of t. So we can rewrite this whole thing as the derivative of f of r of t. Now we can employ the fundamental theorem of calculus for a single variable function, and we get this, FTC2 for single variable functions. Boom. And that was the result. So we showed that this line integral is equal to the difference of these two values. Okay, now, next we need to talk about independence of path. So first, let's define a path. I've used the term before, but let's explicitly define it. A path is just a piecewise smooth curve, and it's just what we refer to as a path. It means that it's smooth, or if it's not, you could at least break it up into a finite union of piecewise smooth curves. That's the idea. And so what do we mean when we say path independence? So a vector field f, if it's a continuous vector field on a domain D, we say that the integral of f over a curve C is path independent, or independent of path, if the integral of f over C1 is equal to the integral of f over C2 for any two different paths in D that have the same initial point and the same terminal point. Okay, so that's a bit of a mouthful. This is when I want to throw up the thinker for a minute, and I want you to read this definition to yourself a couple of times just to see what it's saying, okay? And while we're at it, since you're thinking about it, say it out loud too. So read this out loud to yourself or to your peer or to your colleague or to your dog or your cat, just to give your brain that feedback and think about what it means when you say it out loud. Okay. All right, so just to kind of summarize things, what we say when we talk about path, or what we mean when we talk about path independence, is that the value of this integral doesn't change no matter which path you take between points A and B. So for example, if I had a point A right here and a point B right here, and then I had a path connecting them, maybe this one right here, we can compute a line integral over that path. But there's more than one way to get from A to B. We could get from A to B in this way, or we could get from A to B in this way. Maybe I should do one that is actually smooth. There we go. That way, or we can compute a line integral from A to B by going, this way, right? So the meaning of path independence is that it doesn't matter which one of those paths you integrate over, the integral is going to give you the same result. All right, that's path independence. So now suppose C1 and C2 are two paths that have the same initial point A and terminal point B. And we saw that in general, this will not be the case. And I think maybe if I was drawing this picture, hopefully it kind of like made you tip your head a little bit like that seems a little bit specious. I don't know if that's actually true. Well, remember, in general, it is not true. And in general, it is not true. If I want to integrate over this path, it'll be a very different result than if I integrated over this path instead. So generally speaking, it is not true. Path independence is not a universal property of line integrals. And we're going to see exactly when this property is true. And we get that from a corollary of the fundamental theorem for line integrals. So here it is. If your vector function f given by the gradient of f is continuous and C1 and C2 are smooth curves with the same initial and same terminal points, then the integrals are equal, right? So this is one of the conditions that we have here. In other words, this says that the line integral of a conservative vector field is independent of path. This is the big takeaway. This is a corollary of FTL. Essentially, if you have a conservative vector field and you want to compute a line integral between any two points, A and B, here's A and here's B, it actually will not matter which way you go. It will not matter which path you use. The value of the line integral will be the same, as long as your vector field is conservative. That's the thing. That's the catch right there. All right. Now, we need a couple more definitions because we're going to start to look at this connection between path independence and conservative vector fields, but we need to build up some additional conditions to draw the explicit connection. So first we need to define what a closed curve is. So a closed curve is just a curve whose terminal point coincides with its initial point. So very simply put, a closed curve is a curve that goes back to where it started. That's a closed curve. Right? The terminal point and the initial point are the same. That's a closed curve. Now we have this extra theorem here. So this one we're actually going to prove. It's a biconditional, so there's actually two directions that we need to prove here. And the theorem says this: if your integral is path independent, then the integral over any closed curve is 0 for any possible closed curve in your region D. But it also says the other direction. It says if it turns out that your line integral is 0 for every closed path, then your integral is path independent. So this is an if and only if statement. Path independence is equivalent to saying the integral is always going to be 0 for any closed path. That's what it's saying. Let's prove it so we can see that this is actually true. And we're going to do both directions separately. So here's the first direction. Let C be any closed path in D. We can parameterize it by R of t. And the first thing we're going to suppose is that our integral is path independent in D. So we're assuming path independence first. And then we're going to show that that means that if you integrate over a closed curve, you're going to get 0. All right, so choose any 2 points A and B on a curve C. All right, C is a closed path. Maybe I'll draw a little picture here. Let me do this. There we go. So here's our curve C. And what you can do is you can pick any 2 points A and B on that curve that you want. Maybe I'll pick this as the first point and this is the second point. So this is A, this is B. All right, that's what we're doing so far. Now, we're going to rewrite this curve C as a union of 2 separate curves. That's the next thing we're going to do. And we're going to let C1 be the path from A to B. So C1 is basically this path right here. Oops. C1. And then C2 is going to be the path from B to A. So C2 is going to be this path right here, C2. There we go. Now, let's look at our line integral. So here it is broken up. Our line integral over the curve C, we can rewrite it as a line integral over the union of these 2 curves, which we can then split up into a sum of 2 integrals using finite additivity. And then what we're going to do is we're going to use that result from the previous section about line integrals. Remember, if we change the orientation of the path, then the value of the line integral is going to change, or it's going to switch. The sign of the line integral is going to switch. So here, this is equivalent to this. That's what I'm saying. So integrating over C2, meaning going from B to A, is the same thing as integrating over the opposite of C2 from A to B, but you got to change the sign. So not exactly the same, it's opposite in sign, all right? However, remember that the initial and terminal points of C1 and negative C2 coincide. So remember the initial point of C1 is A, right? And then that is now going to be the initial point of negative C2, right? So here's C1 and here's negative C2. So the initial point and the terminal points coincide on these 2 curves right here. Right, but remember, we assumed path independence. So if you're path independent, that means that the value of the integral is the same. So the value of this integral is the same as the value of this integral. And if we're taking their difference, we're going to get 0. There it is. So in other words, if we assume path independence, then the integral over any closed curve is going to be 0. That's the first direction of implication right there. So we just proved that. Now let's do the other direction. So we're going to assume the other direction. Suppose that this integral is 0 for any closed path C in D. So maybe even this one. There you go. Kind of the same thing. We're going to let A and B be any 2 points in D. Sorry, let me get rid of that. Maybe I should draw D. Okay, pretend D is like the screen, the whole region, right? Let's pick any 2 points, A and B. And then we're going to create any two paths, C1 and C2, connecting A and B. So maybe C1 looks like, oops, where'd you go? There you go. Maybe C1 looks like this, right? And then we're going to make C2 will go like this. Here's C2. All right. Now what we're going to do is we're going to define a curve C as the union of these two curves, but we're going to change the orientation of C2. So remember, C2 went from A to B. So negative C2, the opposite of C2, is going to go from B to A. So that's what we're doing right here. All right. Now, because we assumed that this integral is going to be 0, we can start with that. But we can rewrite this integral as the integral over the union of these two curves. And then we can split it up into two integrals using finite additivity again. And then we get this right here. So negative C2, it's the same thing we did before actually, right? So if we change the orientation of this curve, it changes the sign of the integral. So we get a negative right here, right? So that's the piece right there. Changing the orientation changes the sign of the line integral. All right, now this is pretty much all we needed because what we have is that this difference is equal to 0. So that means that these two integrals are actually equal to each other. And that is the definition of path independence. Also because C1 and C2, or sorry, C1 and C2, oh yeah, path independence. These two integrals have, yeah, these integrals are equal to each other, so it's path independent. The integral's path independent. All right. Okay, so now we've proven this. We've proven that path independence is equivalent to the line integral being 0 over any closed path. Now let's talk about conservative vector fields for a minute. Okay, so the line integral of any conservative vector field is independent of path. So it follows that the line integral of a conservative vector field over any closed path is going to be 0. That's the combination of what we just figured out right now. So what does this mean physically? Physically, this means that the net work done by a conservative force field as it moves some object around a closed path is going to be 0. And this makes sense because really the displacement is 0. So you have to kind of think of this in terms of imagine there's a conservative force field and you want to push this object around in the force field. Well, if you push an object around and you end up back where you started, the displacement is 0. And so the net work that you've done is 0. That's really what this is saying. This is like mathematically encoding that idea. Now what we're going to do is we're going to get the necessary conditions for the converse, the other direction of corollary 1. So let's refresh our memories about corollary 1 here. This one. So this one said this. The line integral of a conservative vector field is independent of path. All right? That's kind of the same thing we were just saying a minute ago. The question is, what conditions do you need for the other direction? Like, is it true that if your integral is independent of path, then you must have a conservative vector field? Possibly. But turns out there's some extra conditions we need. Not super strong conditions, but conditions nonetheless. So let's get back to that. Couple definitions. One, we need a more rigorous definition of what an open set is. So we've been talking about open sets before. You used them back even in Calc 1 and before, open intervals, things like that. So how do we rigorously define what an open set is? An open set is called open if for any point P in your set, there's a disk centered at P that lies entirely inside the set D, right? So let me draw a picture of this for a minute. Let's say here is okay, I'm going to use a dotted line here. Here's my set D. Now, the reason we can say D is open is because you can pick any point that you want in D, maybe this point right here, and there exists an open disk that lies entirely inside of D, or a disk that lies entirely inside, just like that. And if you can do that for every possible point in your set, then your set is considered open, right? The key thing is this, the lying entirely inside of D. So for example, a set that even includes one of its boundary points cannot be considered open, because if you put your center at that boundary point and you draw a disk around it, the disk will reach inside and outside the set. So Open sets are very special. They're basically like, they're unions of a bunch of open disks. That's the idea. Okay. Now, what does it mean to be connected? So a set D is called connected if any 2 points in D can be joined by a path that lies inside of D. So let me give you an example here. Here, this set right here, there we go. This set is connected. And the reason is because it doesn't matter where you pick 2 points, you can draw a path that connects them, just like so. Or if you've got like a point here, you can connect it to these points here. So it's connected if you can connect any 2 points without leaving the set. Now, for comparison, get rid of this one here. For comparison, think about this set right here, the union of these two sets. Okay, so let's say that our set D, maybe I'll call this D1 and this is D2. We can say D is the union of D1 and D2. Well, if I pick a point over here and a point over here, I can't connect them with a path without leaving the set. So this is a set that is not connected at all. Yep. Okay. Now, open set, connected set. Why do we need this? Because this is going to give us the conditions for the converse of that theorem. So here it is. Suppose that F is a vector field that is continuous on an open connected region D. Now, if your integral is path independent in D, then F must be a conservative vector field on D. In other words, that means there is a potential function F such that the gradient of F is equal to your vector field F on the region D. All right, so this result combined with the previous result, corollary 1, really yields that the only vector fields for which a line integral is path independent are conservative vector fields, as long as your region is an open connected region. That's the one catch. So if you've got an open and connected region, then the only vector fields which are path independent are conservative vector fields, and vice versa. All right, that's the idea. Now this one, we're going to go through the full proof. You can also read this proof in the book, but this is one that is definitely worth proving because the techniques are really, really useful. So math majors, make sure you pay attention to the proof techniques that we use here. Here we go. Oh yeah, another note, we're going to prove it in R2 just because it's easy to show in R2, but the technique can be readily generalized to any number of dimensions. And again, you can try that. You should try. Math majors in particular, follow the technique of the proof and then see if you could understand how to generalize it to any number of dimensions. This one is a little bit trickier than the last one, but the idea is basically the same. You just have to think about how you would describe the open disk and how you would describe the curves. That's basically it. So here we go. In R2, so back to the plane. Let D be an open and connected region in R2. Let AB be any fixed point in D. Okay? Suppose that our vector field F is continuous on D, then we claim that the potential function F that we seek is given by this integral for any point x, y in D. All right, so this may be a little bit weird at first to wrap your head around, but remember, we're doing a line integral. We're just doing a line integral, and we're computing the integral from this point A to the point x comma y. That's basically what this is doing, right? Now, this is kind of like those functions that are introduced back in Calc 1. I mean, they are very similar, where the function itself, like the thing that is changing is this upper bound of the integral. Notice the input of this function is x comma y, right? It's two variables. Well, the integral here, the thing that is changing is this upper point, the terminal point of this curve from a comma b to x comma y. That's what's changing. So this integral itself is a function of x and y. It's a function of that terminal point. That's the idea. All right, so now that we've got that set up, because we're assuming that this integral is path independent, it doesn't matter which path we take from a comma b to x comma y. So let me repeat that one more time. We assumed that this is path independent. So it doesn't matter which path we're taking from here to here, the value of the integral will be the same, right? The reason that's important is because that's actually what gives us a well-defined function. So one thing your previous math instructors may not have mentioned is that if you do want to define your own function, you need to actually verify that it's well defined. Well-defined essentially means that it doesn't matter what representation of input you use, you still get the same result. That's what this is saying. And that's exactly what this path independence gives us. So if you're path independent, it doesn't matter which way you go from A comma B to X comma Y, you still get the same result. So that means this function that we've defined is actually well defined. We can call it a function and we can investigate it as a function. Now, since D is an open set, that means there exists, here's D, by the way, that means there exists a disk entirely contained within the set D, just like this. Now what we're going to do is we're going to choose any point x1, y in the disk, and we're going to choose it so that the coordinate here, x1, is strictly less than x. So very much the picture. Let me zoom in for a minute. Right, here's the point x comma y. We're just going to choose a point that's directly to the left. That's it, directly to the left of that point. And the x coordinate of this point is going to be x1. That's what we've got going so far. Now we're going to define the path C as the path that goes from A comma B to this point, x1y, and then goes from x1y to xy. So the union of these two paths is what we're calling C, all right? That's the setup. All right, now let's investigate. If we look at our potential function, f, our potential function f, and we look at the line integral over this curve C, we can again split it into a sum of two line integrals by finite additivity. And then what is the curve C1? It's just the curve that goes from AB to x1y, so right here. And then what's the curve C2? It's the curve that goes from x1y to xy, just like so. All right. Okay, so I hope everyone's still with me. This is what we just had on the previous slide. I'm just copying it again. Now, here's where things get cool. The first integral right here, this one right here, is independent of x. This integral does not depend on x. You'll notice here, x1 is a fixed point. x1 is a fixed point, so it is not varying. This integral does not depend on x, just depends on y. So consequently, when we compute the partial derivative of this integral, it's going to be 0. So let's go through that. We're going to compute the partial derivative of little f with respect to x. So we're doing the partial derivative of this sum of integrals. Now, the partial derivative of this integral with respect to x is 0 because it doesn't depend on x. It's a constant with respect to x, right? And then what we're left with is the partial derivative with respect to x of the second integral right there. Okay, so I hope that makes sense. If it doesn't, please do ask questions in class and I will be happy to go back through the proof. Let's continue. Now what we're going to do is let's write our vector field f as PIQJ, just like the standard structure. So that way we can rewrite this remaining integral here like so, just like that. Now here's the thing, on this line segment that you see right here, remember this is the line segment that goes from x1y to xy. It's this line segment right there. On that line segment, y is constant. There's no up, there's no down. Y is constant, so that means that dy equals 0. This thing equals 0. What we're going to do is we're going to parameterize this line segment with a parameter t, where t goes from x1 to x. And then we can rewrite this as a single integral. I'm sorry, a variable of a single, oh my gosh, an integral of a single variable function. So try to follow along with this for a minute. This is going to be 0 because dy is 0. And what we can do is we can parameterize x using t right here. We can basically parameterize this variable with a t. And t is going to go from x1 to x, right? And we've got dt right there. Now we can apply FTC1, and when we compute the derivative of this integral, we get the original function evaluated at the upper bound, which is p of xy by FTC1. Okay, whew. This is a good time to pause and just let this marinate. Don't pause for too long, but let this marinate for a minute. Look at it, think about it, try to make sense of what we just did, because we're about to do it again. All right, here we go. Oh, there we go. All right, so now we're basically going to repeat this process, but we're going to repeat it with a different curve where we have a vertical line segment instead. Remember, we're allowed to do this because the integral is path independent. It's path independent, so it doesn't matter how we go from here to here, the value of the integral will be the same. So we're going to do this whole thing again, and it's going to be pretty much identical. The only difference is we're going to look at things with respect to y. So here's our potential function. We can split it up into an integral over two curves by finite additivity. Then here what we're going to do is, instead of picking a point that's directly to the left, we're going to pick a point that is directly below the point xy. Let me zoom in. So here's xy. We're going to pick a point directly below. And this point we're going to label as x comma y1. So y1 is a constant right now. Okay. Now, what is C1? C1 is the path that goes from AB to XY1, and C2 is the path that goes from XY1 to XY, right here. Now, same kind of argument as before. If you look carefully here, this integral right here is independent of y. It's independent of y. This does not depend on y. So that means if we differentiate this function with respect to y, we compute the partial with respect to y, this integral is just going to become 0 right here. And then what we're left with is we're left with the derivative with respect to y of the second integral right here. That's all that's left. Okay, same kind of thing as before. Here we go. Oop, there we go. Now on this line segment, x is constant. There's no left or right, oops, I did that backward, left or right change. There's no change in x. So that means that dx is equal to 0. Then we can use t as our parameter, where t goes between y1 and y, and we can rewrite this as an integral of a single variable again. So remember, since dx is 0, this term is going to disappear entirely, and then we can reparameterize this in terms of t. And then now what we're doing is doing the partial derivative, or maybe I'll just say derivative of this integral, and by ftc1 again, we're going to get q of xy. Q of xy. So altogether, this is what we have just found out. This is what all those steps were for. We found out that p is actually equal to the partial derivative of f with respect to x. And we found that q is equal to the partial derivative of f with respect to y. So behold, we've written our vector field f as partial f partial x I plus partial f partial y j, or in other words, the gradient of f. The gradient of f. In other words, f is a conservative vector field by definition, and a potential function for f is given by this integral, and that's the proof. Hooray! So yeah, it's a pretty fun proof. I recommend that you read over it, make sense of the structure. It's just a very nice proof. It's pretty elegant. All right? So just to recap everything we've done so far, we just showed that the only vector fields for which a line integral is path independent on an open connected region are conservative vector fields. That's one thing to take away from this. However, we still haven't developed a simple way to determine if a given vector field, at least on R2 or R3, is conservative. So the question is, like, if I give you a vector field, can you tell if it's conservative? It'd be nice if we had a simple way to do that. We showed this is true, but that can be kind of tedious to have to prove, right? We would like a quicker way of showing this. What we're going to do is we're actually going to establish another necessary characteristic of conservative vector fields. And then we're going to show that under some additional conditions on the domain, like the region, that the characteristic is actually sufficient to guarantee a conservative vector field. So there's a couple more pieces we're missing to like guarantee a conservative vector field. So here it is. This is the characteristic that we're talking about. And we're just going to stick to R2 and R3 for now. Things can get a little bit hairier if you go up in the dimensions. And that's mainly because of how curl comes into play here, which we're going to talk about very briefly in a moment. And then you will see it more in the next section. So here is theorem 5. If f equals pi qj is a conservative vector field, and p and q have continuous first order partial derivatives on D, then throughout D, this equality has to hold. Or maybe a little more appropriately, we can say that this difference is going to be 0. This difference is going to be 0. So let's kind of summarize what we're looking at here. If you've got a conservative vector field on some domain D and in R2, right, and P and Q have continuous first order partial derivatives, so P and Q are C1, then what we know is that this difference is going to be 0, right? So it's like the conservativeness of the vector field and the continuity of these partial derivatives give you this result, all right? Now, here's a little note from the future. This value right here, this expression, is actually related to a concept called the curl of the vector field F, the curl of the vector field. I will discuss curl in detail in the next section, and then we'll discuss it again in section 16.5, all right? So more specifically, what is this expression? Well, the value here, the value of this is basically the k component of the curl of the vector field F. And what this theorem is essentially saying is that if your vector field F on R2 is conservative, then it's not pushing anything out of the xy plane, either up or down, right? So if this value is 0, then your vector field isn't pushing anything out of the xy plane in any way. That's what it's saying. The proof is actually very quick, so we'll do this proof right now. Let F be our vector field on R2. Let's assume that it's a conservative vector field that has continuous first order partial derivatives. Because it's conservative, that means there exists a potential function f, so that we can write p as the partial of f with respect to x, and q as the partial of f with respect to y. And then, frankly, by calling upon Clairaut's theorem, we can show that that difference is 0. So what is partial p with respect to y, partial p partial y? Well, it's taking the derivative with respect to y of this. So using our Leibniz notation, this is actually equal to this second derivative. But by Clairaut's theorem, we know that this has to be equal to this. The mixed second order partial derivatives are equal because they're continuous. So because they're continuous, we can switch the order of differentiation here and preserve the value of that derivative, for that mixed partial derivative. Okay, but this is really just equal to differentiating this with respect to x. But this is equal to q. So we get partial q partial x. And we've shown through this long chain of equalities that this is equal to this. Or in other words, this minus this is equal to 0, which is what we needed to prove, right? So if your vector field is conservative, then this has to be true on a domain as long as these are continuous and so on and so on. But that's the idea. Why is this so handy? Well, I think I show it here. Do I show it here? Yeah, we've almost got, we've almost got the other direction. I guess the reason this one is so nice is because if this is not true, then your vector field can't be conservative. That's the contrapositive of this statement. The contrapositive is, hey, if this is not true, then your vector field can't be conservative. Definitely can't be conservative. But that's not quite what we wanted. Not quite what we wanted. What we would like to know is there a way to determine if a vector field is conservative? And for that, we're going to need a couple more definitions. Here we go. A lot of extra definitions. Good news is the definitions are simple. Pun intended here. So now let's talk about simple curves. So simple curves are curves that don't intersect themselves anywhere between the endpoints. Here's a simple curve. This is not a simple curve. Here's a simple curve. Here is not a simple curve. So simple curves can't cross themselves. That's the idea. Yeah, simple curves don't cross themselves. And then this is just a combo of what a closed curve is. This curve is not closed because it doesn't enclose a region. You can think of it like that. It doesn't, the terminal and the initial points don't coincide, so it's not closed. This one they do, and it's a simple curve. I'm sorry, and it's a simple curve. So it's closed and it's simple. This one is a closed curve. So the initial and terminal points coincide, but the curve crosses itself, so it's not simple. All right? Now that we have this notion of a simple curve, we can talk about a simply connected region. So this is where things get important. A simply connected region in the plane is a connected region such that every simple closed curve in D encloses only points that lie inside D. So in other words, your region D is simply connected if it has no holes and if it's not consisting of more than one piece. So these are like the nicest regions you could imagine, right? Simply connected. They're pretty much like the go-to thing that you imagine when you talk about regions, right? But not every region is so nice. Here's an example of a region that's not simply connected. The reason is that I can pick a curve, say I could pick this curve right here, and that curve encloses points that are not in the region D, namely these points, right? Same thing over here. I can draw a curve right here, and this curve encloses points that are not in D. So this region cannot be simply connected. And if it's more than if it's more than one piece, it's definitely not simply connected, right? Because, like it's just, yeah, it's gonna be split in half, right? So really what we're talking about wait, do I say it on the next slide? I don't. It's a little bit down the way. One way you can interpret this is that your region is simply connected if it has no holes. It can't have any holes in it. That's really what we're trying to go for. And as long as we have this condition, we get exactly what we were looking for. So here is the statement. Suppose you've got a vector field on an open, simply connected region D in R2. Suppose that these component functions are C1, and suppose that this difference is 0, then your vector field must be conservative. Boom. That's the goal right there. So that was like the last little bit that we needed. So this is another moment where I want you to take some time just to think about this particular statement, think about this theorem and what it says. Right? And now the good news is that it doesn't really seem like too much of a condition to need to require, right? We just need our region to be like a simply connected blob. And we need the first order partial derivatives of these component functions to be continuous. And then we need this difference to be 0. And if those things are all true, we're guaranteed that our vector field is conservative. This is great because this gives us a pretty simple way of verifying whether or not a vector field is conservative. So if all these are true, you've got a conservative vector field. All right, now here is the cool stuff. So these results are some of my favorite. Yeah, the new condition is really just that we need no holes in our region. And it turns out that these holes in these regions turn out to be extremely important, extremely important. And the consequences are studied in depth in a complex analysis course and beyond, like in my own research. So in my own research, looking at fractal zeta functions, those holes are basically the complex dimensions of this fractal object. And those holes correspond to poles of the zeta function itself. So you can think of them as asymptotes. You can think of them as asymptotes, that there's basically like a puncture in the region right at that point, okay? So these holes turn out to be critically important later on. And if you want to go down a fun but important rabbit hole, I encourage you to read up about Cauchy's integral theorem and the residue theorem. The residue theorem. Math majors, you will certainly encounter this later on when you take a course in complex analysis. For the rest of you, you will probably end up reaping the benefits of these theorems, and I hope you get to see them as well at some point. Basically, it says if you want to compute a line integral, you can kind of look at what's left over when you integrate around these holes. That's really what it means, because everywhere else, your integral is going to be 0 anyway. That's kind of like summing it up very roughly. So we are actually going to prove this theorem, but we're going to wait until the next section. We're going to wait until the next section when we have a more powerful tool called Green's theorem. Yeah, and then so for now, we're going to accept it as true, but it'll be easier to prove in the next section. All right, now let's do some examples. And these ones I do want you to try. I know I've been doing a lot of talking. Maybe you've had to do some thinking, but you haven't had to do any work yet, right? So I do want you to try this on your own. My question is simply this. Is this vector field a conservative vector field? Justify yes or no, right? So think about it for a minute. Okay, now say something out loud to yourself about how you could get started. What would you try first? Right, and now try to work it out on your own. justify your assertion, my hint to you is think about Theorem 6. All right. And now let's take a look at it together. So remember, Theorem 6 basically says, it says that if you're on a simply connected region and, oh my, geez, I forgot like the statement already. If you're on a simply connected region and these have continuous first order partial derivatives and that particular difference is going to be 0, then your vector field must be conservative. So let's check that. Let's check that. First of all, this vector function is defined on all of R2, and all of R2 is a simply connected region, right? But check this out. If you compute these first order partials right here, partial p, partial y, and partial q, partial x, they're not equal. They're not equal, so their difference is not 0. And that's all we need to assert that the vector field is not conservative. Here I graphed it using Mathematica, so you can do that on your own just to get a peek at it. But because this difference is not 0, our vector field can't be conservative. Yeah, that's the contrapositive, right? That's the contrapositive of Theorem 6, or that previous theorem even. So let's see why for a minute here. The reason this vector field is not conservative is because there's a source right here in the field, and the work produced by the field will be positive if you want to push an object around the source this way, or it'll be negative if you push it around this way. And so what's happening is the work done is not going to be 0. So that's one way to see it. Now, if you did one here, everything would be fine. You would actually get that the line integral here is going to be 0. It's going to be 0 there. But the moment you do one around this source right here, you're going to get a non-zero line integral. That's the idea. All right. Okay, let's do another one. Is this vector field conservative? And this is one that I want you to try too. So think about it for a minute. Say something out loud to your friend or your colleague, your peer, yourself, and then work it out on your own and see if it's conservative. All right, here we go. So we can appeal to Theorem 6. We know the things that we need to verify. We just need to take a look at the region itself and make sure that it's simply connected. We need to look at the partial derivatives, be sure that they are continuous, and then we need to look at that difference, right? The partial p, partial y, partial q, partial x, and see what we get. All right, so here we go. When you compute the individual partials, so if you compute the partial of this with respect to y, this is going to go away and you're going to get 2x. And then if you compute the partial of this with respect to x, this is going to go away and you're going to get 2x. So these partials are equal, which means their difference is definitely 0. Also, the domain of this function is all of R2, and all of R2 is definitely simply connected. There's no holes, right? So by the previous theorem, Theorem 6, this field is indeed conservative. It has to be conservative. This is a conservative vector field. Now, why is that the case? Kind of using the same intuition as before, you can draw closed curves anywhere you want, and you're going to have places where the force is positively or negatively or orthogonally aligned with the tangent of the curve. And so what's going to happen is that's going to start canceling everything out as long as you have a closed curve, right? A simple closed curve. In order for the object to move that way, it's going to be transferring energy back to the field to maintain its trajectory. So the field is conserving energy, right? Like if you try to go this way, you're going to have to fight. But then when you go this way, you're going to get assistance. And adding up all of those changes is going to make the work equal to 0. It's going to make the work equal to 0, so you get this conservative vector field. All right. Now, how do we actually compute these things? So we've looked at characteristics of conservative vector fields. We got some necessary conditions to determine if a vector field is conservative. We've talked about path independence and looking at line integrals over closed curves and so on and so on. Now the question is, how do we actually compute these things? Meaning, how can we actually compute the potential function? Like, how do we compute the potential function to create a conservative vector field? We're going to do an example in 3 dimensions, but the process is equivalent for n-dimensional vector fields. It is definitely a process that is automatable, so it's a good thing to just make sense of how the process works, and then recognize that once you get up to like dimension maybe 4, 5, that it just becomes a bunch of doing the same thing over and over again. All right, here we go. Let's say we have this vector field. Let's find the potential function such that the gradient of f is equal to f, right? So find the potential function itself. This one you're welcome to try on your own, but if you feel like you wouldn't even know where to begin, that's okay. For those that do want to try it, think about it for a moment. How would you find the potential function? What's necessary? All right, you can say something out loud about what you think is necessary for this to be, or for necessary for your potential function. What do you need? And then try to work it out on your own, and we're going to do it together in a moment. All right, so here is the beginning. If we want to find the potential function for this given vector field, we would need the partial derivatives of these things. I'm sorry. We would need the partial derivative of our function, the partial derivatives of our function to be these things right here. In other words, we need this to be true. So if there is such a potential function, if it even exists, right, then it must be the case that the derivative of that potential function with respect to x is equal to this component function. And the derivative of that potential function with respect to y is this component function. And the derivative of this potential function with respect to z must be this potential function. So it's a lot of requirements, right? But that's basically what it means, because that would mean that the gradient of little f is going to be our vector field. So these are the conditions that must be satisfied in order for the function to be a potential function for bold f. All right, that's the basic idea. I numbered these here just for ease of reference. I'm going to refer back to them a couple of times. I'll try not to flash back and forth too much, but I'm going to have to a couple of times. So let's start with this. If we anti-differentiate that third equation with respect to x, then we get this result. So let me go back for just one moment here. We're going to look at this function right here, and we're going to anti-differentiate it with respect to x. Okay, so anti-differentiate this with respect to x, and what you get is this. Wait, am I looking at the right one? Hold on. Wait. Sorry, not 3. Hold on. I have a typo here. That should be 2. Hold on a second. Let me be sure I don't have a typo. Okay, sorry about that. Yeah, that was a typo. I knew something was off because I was like, where did the exponential go? So anti-differentiating equation 1 with respect to x yields this result. So equation 1 is this one right here. There it is. So if we anti-differentiate this with respect to x, then what we get is we get f is equal to xy squared plus some other function of y and z. So this is an important detail to take note of. Remember, when you compute an antiderivative, it's not unique. It's unique up to some quote unquote constant term, but that constant term is constant with respect to the derivative that you're taking. So here you can consider this like the plus c when you do an antiderivative, but the catch is that this could be more than just a constant. It could be an entire function of y and z. Because if you differentiate a function of y and z with respect to x, you get 0. So when you do these antiderivatives, you have to remember that it's not just going to give you an additional constant, it's going to give you an additional function, a function whose derivative is 0 with respect to that derivative, right? That's what this is saying right here. So now we've got this. So again, we're kind of working through what this potential function would have to be to satisfy those 3 equations that we saw on the previous slide. Now what we're going to do is we're going to take this result and we're going to differentiate it with respect to y. So differentiate with respect to y, and you find that the partial derivative of f with respect to y has to be 2xy plus the partial derivative of g with respect to y. So kind of hold this in your mind for a minute, and I'm gonna flash backward again. Backward again. This is what f sub y has to look like, and this is also what f sub y has to look like. So just comparing the terms here, right? 2xy, 2xy, gy, y of z, gy, y of z. This tells us immediately that the partial derivative of g with respect to y has to be this. There we go. So those have to be equal to each other. And that's what I'm saying right here. Comparing the terms in equation 2, that's correct this time, this has to be equal to e to the 3z. Now we can repeat this process again. We can anti-differentiate this function with respect to y. And then what we get is y times e to the 3z plus some function of z. So by the same argument I was making a moment ago, this could be any function of z, because if you differentiate it with respect to y, you get 0. So now we have that g has to be equal to this, and we can substitute that into what we had just a moment ago. So now we're slowly building this potential function. Oops. I meant this is this. All right, now we're going to continue the process. Now we're going to differentiate this with respect to z. And when we do that, we get that the partial of f with respect to z is equal to this. Now we're going to compare to equation 3. And when we compare to equation 3, we're going to see that h prime of z has to be 0. And so that means h of z has to be equal to a constant. Let me go back to the equations for a minute. Right here. See, there's nothing here, right? There's just this piece, just that piece. So when we go here, this has to be equal to 0. But if the derivative is equal to 0, then that means that your function has to be constant, and therefore we have our potential function. There it is. So we kind of did this reverse engineering process, right? Where we're like, okay, if we wanted it to be the potential function, these partial derivatives need to be equal to these component functions. Okay, if those are equal, what happens when we anti-differentiate? And then what do the results give us? And then we did all these comparisons, right? So in the end, we found this. And it's always fun just to verify that this is correct. So just take this function and compute the partial derivatives, and you should get these component functions back. Let's see that we do. Differentiate this with respect to x, gone, gone, and you get y squared, check. Differentiate this with respect to y, and you're going to get what, 2xy plus e to the 3z, and that disappears, check. And then differentiate this with respect to z, and what are we going to get? That's gone, this 3 is going to come down from the chain rule, and we get 3y e to the 3z, check. So indeed, this is our potential function as required. And that's how you do it, right? So now we know how to compute conservative vector fields. Now let's finish up by talking about conservation of energy. So this is where the physicists will probably get really excited. I hope you do. It's a very elegant result. So maybe you've guessed from the names that have been floating around this whole time that all of this is strongly related to conservation of energy. And now we're going to make that connection explicit. We're going to make it explicit. So here it is. Suppose that our vector field F is a continuous force field, and it moves an object along a path C. C is given by this parameterization, R of T. T goes between A and B. And we're going to label R of A as capital A, that's the initial point. And R of B is B, that's the terminal point of C. So C goes from A to B, just like so. Now, by Newton's second law of motion, F equals ma, we know that the force at a point on C, remember this is the force at a point on the curve, it's related to the acceleration by F equals ma. So we get F equals ma. And remember that the acceleration vector is just the second derivative of the position vector. So acceleration is the second derivative. So we know this, F equals m times r double prime of t. Now we're going to re-express the work done by the force on this object through this calculation. So what we're going to do is we're going to calculate the work that the force field does in moving an object along the curve C. And we're just going to plug in stuff that we already know, and then use one of those properties of of the dot product from way back in chapter 12. I mean, way back in chapter 12. So here we go. Line integral over C. We can substitute in our parameterization, f of r of t dot r prime of t dt. So we've changed our variable of integration to the parameter t. Now remember that f of r of t by Newton's second law is ma. So m times r double prime. Now we can actually factor the m out of the integral by linearity, and we can compute this dot product right here. So going from here to here, I'll say, is actually a result from chapter 12. So if you look back in section, oh geez, is it chapter 12? Man, I can't remember if it's 12 or 13. But if you compute this, remember there's a simple product rule for the dot product, right? So if you want to compute the derivative of a dot product, like so, then you're basically going to use an analogy of the dot product for, I'm sorry, an analogy of the product rule for a scalar product. You're going to get this prime times this plus this times this prime. That's essentially the idea. But then, because you're going to end up getting two of the same terms, you can write it as 2 times this right here. That's where this 2 is coming from. So maybe I can make it more explicit. Sorry, maybe I'll just write it out. What am I saying? d dt of r prime of t dot r prime of t is equal to r double prime t r prime t plus r prime t r double prime t, but that's just equal to 2 r double prime double prime, where did you go, t r prime t. There it is. Oh, dots. Sorry, these should be dots. It's like something feels off here. Those should be dots. Okay, so if you differentiate this dot product right here, you end up getting 2 of these right here. So that way, if you divide by 2, you get what we had before. So if we divide both sides by 2, you get this. And this is exactly what's going on here. So this is right here. So I hope that makes it a little more clear. I know my handwriting's a little messy, but that's how we're going from here to here. Just a clever use of that product rule for the dot product. All right, now another thing we're going to use, another property of the dot product. Remember, if you take a vector and you dot it with itself, then you get the length squared. So r prime dot r prime is the length of r prime squared. Cool stuff. Now what we've got is the derivative of this length with respect to t, but we're also integrating with respect to t. So by the fundamental theorem of calculus, we can just evaluate this at the 2 endpoints and take the difference. So FTC2 coming into play here. Then do the evaluation. You get r prime b squared minus r prime a, oops, typo, squared. Oh, another typo right there. That should be a squared. And I fix it at the end. All right. Now, last little notation change here. Remember that the derivative of the position vector is the velocity vector. So r prime is v, r prime is v. And then now we can split this up and we can write it as 1/2 mv squared minus 1/2 mv squared, or I should say the size of v, evaluated at b here, evaluated at a here. There we go. All right. Now, what is this? We just showed that the work done is equal to this value here. And the quantity that you're seeing in these two terms, half the mass times the square of the speed, that's what's known as the kinetic energy K of the object. So physicists and engineers even, maybe you recognize this before we even got there. That's the kinetic energy. We can denote it by K. And so what we can do is we can rewrite this work equation as the work done is the kinetic energy at B minus the kinetic energy at A. There we go. So that's the work done by the force field in moving an object along C. So it's the change in the kinetic energy at the endpoints of C. All right, so hold on to this for a minute. Now we're going to look at it from a different perspective. Here we go. If we further assume that our force field is conservative, if it's a conservative force field, then that means there's some potential function little f, or if we take the gradient of f, we get bold f. Now, we define the potential energy P of an object at any point as the opposite of F. So this is what we call the potential energy. This is why I've been referring to this as a potential function, like a potential function. So we're going to define P as the opposite of F. So that way, capital F or bold F is equal to the opposite of the gradient of P. I note it here, but the reason that we choose the negative sign for this is just to agree with the intuition that work done against a force field increases the potential energy, right? So it's like if you're, if you're pressing against a wall and the wall is not moving, you're increasing your potential energy, right? And then if the wall were to disappear, you would go poof, like that. So that's what we're talking about. The reason this is negative is because if you're working against the force field, you should be increasing your potential energy. All right. Now, by the fundamental theorem for line integrals, remember, because this is a conservative vector field, the line integral here is really just negative this line integral by substitution, right? And then we can use FTL to just evaluate this at the endpoints of the curve. But this is B and this is A, so we get that the work done is also equal to the difference in the potential energy at the endpoints. All right, now here's the magical part. Actually, I feel like all that was the magical part, but I guess here's the punchline. Here's the punchline. If we put these two work equations together, we have that this is equal to this. So the change in the kinetic energy is equal to the change in the potential energy. Moving some things around, and we get that the potential energy at A plus the kinetic energy at A has to be equal to the potential energy at B plus the kinetic energy at B. That's the total energy. So total energy at A is equal to the total energy at B. This is the conservation that you learn about in the law of conservation of energy. So, in other words, if you're going from point A to point B under the influence of this conservative force field, the total energy remains constant. And that's the law of conservation of energy. And this is why we call it conservative and potential. So I hope you like that result. Very cute, very clean, very nice. All right. And on that note, let's play. So I'm excited to work with you all about this when we do an activity related to it. Thank you for hanging in there for a for a long lecture. If you have questions, please ask in class. I do recommend that you review those proofs because some of those techniques are really handy. But I'll stop rambling here and I will see you all next time. Thank you again for watching.